Hi, my name is Elsie Weissar, and I'm happy to share some of the work I've been doing with the denitrifying woodchip bioreactor here at OSU. During the course of this short video, I will briefly touch on the motivation for the project, an overview of denitrifying woodchip bioreactors, some of the methods I used for data collection, and some initial results and conclusions. Before I begin, I'd like to recognize some key support for this project. The Oregon Dairy Farmers Association provided key funding for the unit installation, and the Oregon Department of Agriculture and the OSU Agricultural Research Foundation both provided support for research activities. To start, I think we can all agree that we need clean water to thrive. Unfortunately, in recent decades, increasing amounts of excess nutrients in our water resources has led to problems such as eutrophication, anoxic zones, and toxic algae blooms in our surface waters. This has grown to the point that the National Academy of Engineering has named managing the nitrogen cycle as one of the great engineering challenges for the 21st century. Agricultural activities can be significant contributors of nutrients to water resources. Runoff and tile drainage from both crop systems and large livestock operations can be sources of large amounts of nitrogen pollution. Over the past decade, denitrifying woodchip bioreactors have been explored as a possible edge-of-field method for reducing nitrogen compounds in agricultural runoff. Denitrification is the stepwise reduction of nitrate back to dinitrogen gas. In the natural environment, each step is catalyzed by bacterial enzymes, with different groups of bacteria producing enzymes for the different steps. The functional concept behind the woodchip bioreactor is that agricultural drainage is channeled through a bed of wood chips. The chips provide a growth medium for bacteria, which then, hopefully, consume the nitrogen compounds for their metabolic processes, ultimately returning the nitrogen to the atmosphere as dinitrogen gas. However, if the conditions are not quite right, or the necessary organisms are not present, the denitrification process can be incomplete, and byproducts such as nitric and nitrous oxide can be released, both of which are powerful greenhouse gases. To provide a sense of scale, I've included a picture here of a field installation in Iowa. These units have been studied quite a bit in the US Midwest and also in New Zealand. However, little has been done in the type of climate we experience here in Western Oregon. To look into how a woodchip bioreactor might work in our climate, a unit was installed to treat tile drain runoff from the OSU dairy farm. It is located just south of Campus Way, between the solar array and the covered bridge. The tile system drains about 40 acres of forage field that is used for forage harvest and rotational grazing. The soils are a mix of silt loam and clay soils, and liquid manure is spread seasonally when weather conditions permit. For those that are interested, I've provided installation details in a separate video on my conference webpage. For this part of the project, we collected daily inlet and outlet water samples using ISCO automatic samplers. All water quality samples were tested in-house using colorimetric methods. For nitrate and nitrite, we used a vanadium reduction method, and to test for the ammonium ion, we used a sodium salicylate nitroprusside reaction. The bioreactor has now been in operation for 2 winter seasons, and I'm happy to present some of our initial findings. But first, some context. Our woodchip bioreactor is primarily driven by rainfall. These plots show the inlet and outlet hydraulic head alongside the year's rainfall. The key thing to note here is that once the soils are saturated, the unit experienced what I call semi-steady state conditions with respect to flow. For the first season, I left the stop logs in the control boxes at the maximum height for the entire season. For the second season, I periodically changed the gates to change the flow rate through the bioreactor. These plots set the inlet and outlet nitrate concentrations against the precipitation plots. The nitrate inlet concentrations do seem to show some connection to the rainfall, which would make sense as nitrate is very easily transported with water. The other key thing to note here is that once the reactor got past an initial startup phase, concentration reductions are significant and continue through the end of the 2019-2020 season, and start right up again in December of 2020. This continues until a flow change is made at the end of January. After the flow change, there seems to be a 2 to 3 week period of adaptation, at which point steady reductions occur again, but at a much smaller percentage. This slide shows the nitrite concentrations below the nitrate concentrations from the previous slide. As you can see, the nitrite concentrations are much smaller, and whenever there's some sort of a spike, it does tend to relate to what's happening with the nitrate concentrations. Ammonium concentrations were also much smaller, though we do find a significant seasonal increase in the late spring. The most interesting thing about the ammonium concentrations is that there do seem to be some consistent reductions, which is surprising. The internal conditions in the bioreactor are inherently anaerobic, so conditions are not really conducive for normal ammonium oxidation. Since the cold season operation is the current interest, there are 3 key date ranges to look at: winter of 2019-2020 and December-January 2020-21, which were operated at the maximum hydraulic retention time. And then February-March of 2021 were operated at a shorter hydraulic retention time. Looking at the combined stats for the maximum hydraulic retention time dates, we find nitrate concentrations are reduced to below 10 milligrams per liter with a 65 to 70% reduction. For the shorter hydraulic retention time, nitrate reductions are much smaller, with outlet concentrations of about 17 milligrams per liter and only about a 20% reduction. In addition, nitrite shows a tendency to increase at the shorter hydraulic retention time. While the magnitude is small, this could possibly indicate a shortened denitrification chain. If we look at these same periods in terms of total nitrogen reduction, where concentrations are multiplied by the estimated flow rate, one sees a similar pattern. The periods with the maximum hydraulic retention time show a greater percentage of nitrogen removal, 53 and 70% respectively, and the shorter hydraulic retention time only shows a 24% reduction. However, it is interesting to note that, because of the higher flow rate, the magnitude of the total nitrogen removed at the shorter hydraulic retention time is comparable to the nitrogen removed at a longer hydraulic retention time. So, some initial findings from our project include: 1. Denitrifying woodchip bioreactors can work in a Mediterranean climate such as that found here in Corvallis, Oregon, providing good reductions in nitrate concentrations, even during the colder winter runoff season. In addition, it appears that a hydraulic retention time of 22 to 30 hours will provide good cold season nitrate reductions. However, it must be noted that this is significantly longer than the 10-hour minimum hydraulic retention time recommended by the NRCS and may require some different engineering design guidelines. And there is one caveat to keep in mind. It is known that higher reductions tend to occur in early years of operation due to high levels of readily available carbon from the fresh wood chips. This raises questions of what kind of reductions can be expected in later years. Some questions for further study include looking at the gaseous phase elements during the cold season. Is complete denitrification occurring? Also, significant ammonium reductions were observed, but the exact mechanism of how that would occur is unknown and should be investigated. And last but not least, large reductions can be obtained at longer hydraulic retention times, but the possibility of producing undesirable compounds should be investigated. So that completes the overview of my denitrifying woodchip bioreactor project. Thank you for your attention. Again, if you're interested in the unit installation details, that can be found via link on my conference webpage. Thanks again.